Okay, are we ready? Yes, it's time. So welcome to the tutorial here. Before we start with the on-hands, I will just give you a few more background information about the software and what you all can do with it so that there is a sort of general concept. And then I will guide you through structure-based modeling. I will show you how you can use docking in Ligand Scout. I will show you how you can use binding affinity estimation, directly change your ligands, because this will be something that you might want to do in your challenge, right? You need to find out of the molecules which are active ones. So, not to waste too much time here, uh, I showed you this already in my lecture. So it's a fully integrated molecular design package. Pharmacophore-based modeling, structure-based pharmacophore-based modeling, ligand-based modeling, virtual screening, docking, library creation, etc. And we also have KNIME extensions. So if you want to use the KNIME nodes because you want to plug in different software tools together, for instance, generate Ligand Scout pharmacophore models, do the screening, then do docking with Glide or machine learning and so on, you can do this in the KNIME platform. So IntelliGant is more than 20 years old. Actually, it was incorporated in 2003 in Vienna. So it's 2.5 hours from here. On a street that is called Maria-Hilfer-Straße, is the office of the developers. And this has been turned into a pedestrian zone. So this is very nice now. In the evening, you can sit outside on the street and enjoy the evening. Something very, very, very important is...
Is it visible? No, it's not visible. Okay.
is maybe you write it on a paper and hand it over around so that... Yeah. So very, very important, the help, right? There is a full user manual of Ligand Scout in the installation directory. So if you go to the installation directory, there's a subdirectory that is called MISC, MISC. And in this subdirectory, there is a PDF of some almost 200 pages where all the information about Ligand Scout is the user manual with links and explanations, also about the command line usage, etc. But there's also an online help system in the software. So if you want to look at something in the software, you can go to the help menu, and then you have this chapter overview, and you can go down and search for things in this help. And there's a third help program, an independent graphical user interface that you can start outside the software. It's called Ligand Scout Help executable or DMG for app for Macintosh. So you have 3 different ways of accessing this help. And don't hesitate to look at the help menu and read the manual, right? Sometimes it's important also to read the manual. So some of the unique features of Ligand Scout are in structure-based pharmacophore modeling. So you can generate interaction models, pharmacophore interaction models of protein-ligand complexes with a click of a button. You load your X-ray structure, you load the cryo-EM, you load your NMR structure, you zoom into the binding site, the Ligand Scout identifies co-crystallized ligands, puts a yellow box around it. This is the so-called core. You click on this yellow box and Ligand Scout will zoom in, and then you can do structure-based pharmacophore modeling with a click of a button. You can generate tautomers in this binding site and evaluate different tautomers if you like. You can analyze side chain rotamers. Sometimes it's not clear if an asparagine is like this, or which histidine you have, the NH, right? So you can generate this on the fly. Then, apart from the structure-based modeling, you can have ligand-based modeling. So you don't need the structure of your target, you just need active ligands, and you can automatically ask for structure-based, ligand-based pharmacophores by doing conformational analysis and overlaying the ligands on top of each other automatically to generate ligand-based models. You can do pharmacophore-based clustering of your data set to be able to generate very meaningful pharmacophore models. You don't have an upper limit of features. You can have several features per atom. For instance, if you have an OH, the oxygen can act as an H bond donor, but also as an H bond acceptor, right? Two ways. So LiganScout can take care of this, of course. And also you can have exclusion volumes. These are space limiters around your pharmacophore automatically in a ligand-based pharmacophore model. And in virtual screening, it's the opposite than you have with Glide or Moe or Discovery Studio when you do pharmacophore-based screening. The more features you have, the faster it gets, because it has a very smart indexing system that will throw out all molecules in the database that cannot possibly match. So it will not try to align them if the feature count is not fulfilled. So this makes screening of very large libraries very efficient. Speed and accuracy increases with the number of features. So what kind of features do we have? This is an overview of the pharmacophore features. We have features that have vectors. If there is a direction information, so if we know exactly where the ligand, where the H bond acceptor sits, where the H bond donor sits, we can draw a vector. But it can also be open with only a sphere if we don't want to restrict it. We have H bond donor and acceptor. We have positive ionizable and negative ionizable. So a carboxylic acid, for instance, or a tetrazole, C-substituted tetrazole, will be recognized as a negative ionizable feature. Also, if it's not charged. So you avoid that you have to prepare your ligands, because irrespectively of the protonation state, it will be recognized as a negative ionizable or as a positive ionizable for amines, for instance. Then you have this very famous hydrophobic feature that is there. Then you have aromatic rings that recognize aromatic interaction, sandwich or T-shape with a certain deviation, and pi cation interaction. So if you have an aromatic ring and you have an amine somewhere, this will be recognized as a p cation interaction. Then what is absolutely unique, we have halogen bond. You know what a halogen bond is? Chlorine, bromine, and iodine have the sigma hole on top of their head where the connection is, and this is delta plus. And so this will interact with a lone pair as a so-called halogen bond. Fluorine will not do this, right? Very important. Then we can recognize interactions to metals, to iron, zinc, magnesium, and manganese. These are the 4 ions that are implemented at the moment. And what is also very nice is a covalent feature. So if we have covalent binders, LiganScout will put a covalent feature in this place. And when you do screening, it will recognize chemical groups that can create a bond, like Michael acceptors or halogenated heteroaromatics and so on. Very interesting thing. And the exclusion volumes, where we can make a code of exclusion volumes to limit the size of the thing. Yes, this is the halogen bond. This is the halogen bond. Exactly. And the halogen bond is actually, it is here, XBD it's called. Halogen bond donor, because of the sigma hole. And what is very important for you, because this tutorial today is only a little bit more than 2 hours, so we cannot possibly cover everything that you can do in the software. There are tutorial cards, and you should have received links from Professor Berka and Professor Polischuk with the information where you can find these PDFs and the material for the tutorials, right? So please download this and use this for further study. Very nicely described tutorials where you can go quickly through all these different things. So I don't want to go too much into more details here. It's a molecular design platform. You design molecules, generate predictive models, understand SAR, can find hits in libraries, filter and prioritize them, etc. It runs on Windows, Mac, and Linux. So these are Windows machines. These are pretty good computers. I remember from last year. It runs very well on the Mac M processor. So if you have an M4 at home, this will blow your mind. And you can do a lot of other things. I showed you already these MD simulations, and I will show you a few things when we have to relax. But first, we will go really now into the details, right? And I will stop my presentation here. Oh no, I just wanted to mention one more thing here. There's one more thing. There is also in the Ligand Scout installation directory, there is a bunch of executables, the so-called command line tools. A lot of features that are in the GUI of Ligand Scout, in the graphical user interface, you also can access from a command line tool. It's an executable. For instance, you have iFarmGen. They all start with I, not because I'm an Apple fan, but because it's from Intelligent. So iAlign or iFarmGen. iFarmGen is the command line tool that will generate structure-based pharmacophore models from a PDB input that you have. You can download a whole number of PDB files and run a script that goes through all the PDB structures and generates automatically a pharmacophore model of all the ligands in these crystal structures. For instance, or Espresso is the ligand-based pharmacophore generator that you can run from the command line. iScreen is the virtual screening, so you don't need to block your user interface. Also, it's multi-threaded, and when you do screening, you still can go back into the structure-based view. But even using less resources of your computer or using other computers in a cluster, you can use the command line tool iScreen. And all these command line tools are described in Appendix 6 of the user manual, and all the arguments that you can use for input, output, options, etc., are listed in detail. So if you type in help minus, for instance, help IDB merger minus all, then you will get in the help in the command line in the in the shell, you will get all the parameters. Okay. Now let's finish with this, and I will just stop the presentation here, and I will go to Ligand Scout. So you should all start your software, and I will go to the things and explain this to you. Hide video, hide, floating. Okay. Okay, so this is how Ligand Scout looks like when you start it. And now we have to decide, actually, do we want a bright or a dark color? So you can switch the colors by Control L. Control L will switch to black, dark, and will switch back to white. So you can set it to the color you like. Sometimes it's when you're in a dark room, it's nice to have a dark black background. If you want to make pictures, you stay with the white background. Okay. Next thing is, where is help? Help is a specific menu. On the Mac, it's here upstairs. Help. You can go Ligand Scout help. You can go about the system, about Autodoc and license information. So this is the thing that I showed you already. So don't hesitate to consult the help. It's very helpful. Okay. Next thing, there are two types of menus. There are these quick menus that are these symbols here that are context sensitive. So if you cannot do something with this menu item, it will be grayed out. It's only in color if you can do something. And when we do different operations, you will see that some of these points here, these menu items, will light up. At the moment, the only thing that is active is undo and the molecular editor. These are things that you could start right from the beginning. Another thing, because we will always use a gender, I will say he or she or it. I mean, what shall I use for ligand scout? She? She, because she does really well. You will see. And if she's not doing well, then we can say he. Okay, just a little joke. Okay, so no, but it's really I love to use it myself. So it's a great program. Now I want to introduce you to the concept of the viewers. You have 4 different perspectives in Ligand Scout, and they are here named. This is the structure-based perspective. This is the one that you start with. In this perspective, you can load PDB structures, protein structures, protein ligand complexes, and you can analyze them. You can also load empty proteins and investigate if there are pockets. And if there are pockets, what kind of pharmacophores might be there. And I will show you how this works. You can also load SDF files, collections of molecules, into this perspective. Then there will be a table that shows up, and you can go through the molecules. This is the structure-based perspective. You can do the same in the ligand-based perspective, but the appearance changes a little bit. In the ligand-based perspective, you have always a 3D view. This is the big one here with this little symbol in the middle. A 2D view where you would see the molecules in 2D. A table view. Another view here where the pharmacophores that are generated are listed. And another hierarchical view that was also there in the structure-based perspective. And what is important, you can resize all of these windows. If you want to have a bigger 3D view, you just go with the mouse and just move this over here. And you can also change the size of the table, for instance. Typical effect here when I show it. Okay, so this I didn't like. I go back, and now it's there. So I think this has sometimes when I use a video software like Zoom, sometimes there are artifacts that are coming in. So this would not happen when you don't use Zoom. Okay, the third view that we have is the alignment view. It says what it is. In the alignment view, you can align molecules to molecules. You can align molecules to pharmacophores. You can align pharmacophores to molecules. You can align pharmacophores to pharmacophores, right? Everything what has to do with alignment. And in the final one, this is the screening window, screening perspective. You load in databases, you load in pharmacophore models, not only one, you can have multiple models, and then you can perform virtual screening, right? So if you want to use, for instance, a pharmacophore model that you generate in the structure-based view, the structure-based perspective for screening, you just need to copy this model over to the structure-based. If you want to use a ligand-based model, you copy it over to the virtual screening perspective. And how you do this, I will show you. Let's start with one example. A first example here to load in a protein X-ray structure. And for this, I mean, you can, if you are interested in a specific protein and you know the PDB 4-letter code of this protein, just go ahead and start with your own protein. I always start with a kinase inhibitor, CDK2 kinase inhibitor, where we have data sets and we have provided these data sets for you, but you can use whatever you want, right? So I start with the 4-letter code 1KE7. And then, so I type in this code. And what you do as next is you say download 1Ke7. So LigandScout, now she connects to the PDB server and downloads the structure. While she downloads the structure, she analyzes, is there a ligand in this structure? If there's a small molecule ligand, she draws a yellow box around it and interprets already the ligand based on the geometry of the ligand, because you know in the PDB there's only information on heavy atoms. There's no information on hydrogens. There's no information on the type of a bond, if it's a single bond, a double bond, a triple bond. She analyzes this based on the geometry of the molecule and puts the right things. Sometimes she can make a mistake. Then you need to correct it, but it's very easy to correct it. Normally she's right. Okay, now we have this yellow box here. You can mouse over the yellow box and you will, sorry, this was not good. This was up there. So when you move over the yellow box, you will see a 2D representation of the ligand already. That will disappear after a few seconds. So, and when you click on the yellow box, this is the most beautiful thing. She zooms into the binding site and shows you the ligand in the binding site. And with one click of a button, she will generate the interactions that this ligand makes with the protein. And the button to press for this is this button here. This one. Create structure-based pharmacophore. And it takes less than a second, and you have the interactions that this molecule makes with the protein. Now, let's do something. Let's think about the interactions that this molecule could make in theory. Right? And to do this, I will delete the protein. To delete the protein, I select here in the hierarchical window, you see core molecule, pharmacophore, and macromolecule. I highlight this macromolecule and I press the delete key. The delete key is this little X here. Now the protein is gone. Did you all manage to get the protein away? Now I press again, generate pharmacophore. And it looks a little bit different now. Could you follow? We deleted the protein by selecting it in the hierarchical view, highlight it, and then go to the little X, or press the delete button on your keyboard to delete it. And then I generated again a pharmacophore model. And now this model looks like that. So, yes? Exactly, exactly. So he realized what happened. In this case now, she does not know what the environment is. She just knows this is the ligand, and when I press the button for the pharmacophore, she puts all the features that are possible for this ligand. And what are these features? We can look at them. This one here is a hydrogen bond acceptor. The nitrogen on this oxazole can accept a hydrogen bond. The oxazole is an aromatic ring, therefore we have this little ring here. This aromatic ring is an aromatic ring and hydrophobic. Therefore, we have the ring and the hydrophobic feature. This NH is a donor, and it's rigid. So we know she knows exactly where the acceptor sits at the end of the vector. Here would be the acceptor. Then the keto group here of the amide acts as an acceptor, but she does not know from where the H bond would come. Therefore, she puts a sphere. The other one is also rigid again, because there's a double bond here, So there's a vector, and so on. So we have the aromatic ring with aromatic function and hydrophobic. And here we have two hydrogen bond acceptors because the two oxygens of the sulfone can accept H bonds. But as you said, these are not all the interactions that are present in the protein. So what she does is when there is a protein around, she first checks all the features that are possible, and then she looks, is there on the opposite side of this acceptor, is there a donor in the real range? And if yes, she puts the feature. In the aromatic ring, is there another group in the amino acid sequence that can make an aromatic interaction? And if not, then there will be no aromatic feature, only the hydrophobic feature that we saw before. When you remember what the pharmacophore was looking like, we had nothing here. We had two hydrophobics. We had donor, acceptor, donor, and one acceptor on the sulfone, but not every feature is filled, right? So this is a very important concept. Ligand scout, when you do structure-based pharmacophore modeling, only those features are taken into account that really are existing. And so how is this defined? Well, this is defined by distances. You need to have a certain distance for a hydrogen bond, a certain angle, and in the preferences, you can see all these settings. So there is one thing here. On the Mac, it's called Ligand Scout Settings. In Windows, it's under Edit Preferences. And these preferences, there's a lot of things that you can set here. Well, let's go to the first one, structure-based. And here you see for all different interactions, the distances and angles that are by default. These settings are good settings, right? But sometimes you might want to be a little more flexible because maybe in one X-ray structure the resolution is not good enough, and so the distances may be a little bit too high and the feature will not be recognized automatically. You can change the settings in the preferences and redo the generation. So each page that you have here, you can do different settings. And if you don't remember anymore and you want to go back to the default, you can press default. Then it will just reset to the default values of this page. If you put all defaults, it will reset all the default settings of all parameters, right? So this is very helpful because it takes away your fear that you might change something that you don't know how to get back to it, right? So this is easy. Okay. So now let's go back to the original, and we can do the undo. So we undo. Now we have the pharmacophore model that was from the protein. We can also undo the deleting of the protein. And here the protein is back. Very good thing, this undo function. Sometimes it takes memory, of course, because she needs to remember a number of steps before. And if you have a big fat computer with a lot of memory, no problem. If you have not so much memory, you can run into troubles. But in the preferences, you can say how many steps she must remember, right? Let's go back to the settings. Let me see if I find it. It's settings. Where is it? Is it under programs? No. Is it under? Where is it? Huh. Is it possible that I don't? In the program and network should be. Yeah. There it is. There it is. Wait a second. Undo levels. Yes, thank you. Undo levels. Here, 10. 10 is the default, right? I can go higher. I can go here to 50. This is the maximum. but this is not a good idea. Right, so this is here, right? Thank you, thank you. My eyes are, with the glasses, I only see in the distance and, okay. So important, if you experience performance issues because you don't have enough memory, just go down with the undo level, right? Also, another thing here, Ligand Scout, she is quite a memory hog. She wants a lot of memory. So per core, because it's completely multi-threaded, so all is parallelized, which makes it fast, but each core takes memory. So you should have per core at least 2 GB of memory free that she can use. So therefore, here I only can use 5 CPU cores because I would have 8 cores, but she tells me better only to use 5 because you don't have so much memory. Unfortunately, this Mac has only 16 gigabytes, and a lot is used by the operating system, so 10 are probably free, and so she says 5 cores is enough, right? Be happy with 5 cores. Of course, if you have a big machine with 24 cores or 32 cores or 64 cores and a large memory, you should be really using it, and you will experience incredible performance. But remember this, right? So undo levels and number of cores. When you start it for the first time, she will find out what the best settings are. So I'm curious, what is your settings here?
8 core, 22 gigabytes.
Oh, great, 8 cores. So this is very good. So you will be faster than me. Okay, great. There's also another thing here that you can look at. This is this Ligand Scout server. This is a built-in client, system to connect to high-performance computing. If you want to run, for instance, database generation or virtual screening on a cluster, for instance, you have an in-house cluster, or you want to use the Amazon cloud, you can install a server of Ligand Scout on this cluster and set up a batch system, and then you can run things externally. For instance, you can start the screening of these billion compound libraries somewhere on a cluster, shut down, go back a few hours later, and then collect the results, right? Okay. And everything is documented. You can find documentation about this when you go to the website docs.intelligent.com. So these are the docs, the documentation of Intelligent, and you will find this information there about Ligand Scout Remote, about installation, and so on, help menus. Okay, so now we have this Pharmacophore model that was derived from the X-ray structure as it is. Is this a good idea to do it or not? Well, this depends on the quality of your X-ray structure. If it's very high resolution, if the crystallographer did a good job, then it's fine. What you can do, you can run a short energy minimization to check if the ligand stays in place or if the ligand moves. If the ligand stays in place, this means that it's well refined, right? Because X-ray is also based on force field minimization. So if the crystallographer did a good minimization, fine. If the ligand moves, then this is a good sign that the resolution is not so good. And probably you should really do the minimization and then do the pharmacophore. So I do this. How it's very easy to do the minimization. It's a one button here. Press this button, and it will minimize the energy of your ligand. And you see it moves a little bit. So this is minimization. This is a pure minimization. And only the ligand moves. The side chain and the protein remains constant. But you also can, if you want, but this is not with one button, you can go to molecule, minimize energy of side chains, or minimize energy of core molecule and side chains. So you cannot minimize the core, but you can minimize the side chains and the molecule. And when you do this, so at first I undo the minimization, so it's in the original orientation. And now I go to molecule, minimize energy of core molecule and side chains, and you will see a lot of movement going on. Okay, so at the end, it's not so bad, because at the end it found a configuration. When we now generate the Pharmacophore model, it looks a little bit different, yeah, because the side chain have moved. So we have a Pharmacophore model that is optimized on these two water interactions here, because of course also the water molecules move. We have lost the two donors because this is enthalpically favored, but probably entropically disfavored. So the energy was gone. The two hydrophobics are the same. And this part here has not formed any other interaction. So I'm not really sure. What I suggest, normally I do the modeling with the raw structure, the unminimized one, and then I do a full minimization and I keep both models. And I evaluate both models, how they perform.
Kind of about that. FF94 is kind of older and it's not that hyper. So how would you say if it's worth it now? Or do it external, like with some quantum MM?
Yeah, I mean, if you do this, if you can do this, of course, this is better, of course. Yeah, right. If you can prepare your complexes before you do the modeling in Ligand Scout with a QMMM method, of course. I mean, this is the best you can do. At the moment, we have the MMFF94 and 4S versions in there, and they are good for molecular interactions. So they really reproduce well H bonding behavior, for instance. So this is why I like it. But of course, I mean, this is also flavor. You know, somebody can want to have OPLS or QMM, whatever. You know, but this is, I mean, no, there is also some kind of compromise on that, right? So we did not want to develop a new force field, for sure not. And so we took in our eyes at that time, the best available open source force field, and this was MMF94. Could be debated in the future. We might want to put another one in. Yeah?
Some transitional metal inside of the molecule, because these are some issues in this video.
Yes, this might be a problem. But again, then you should not touch it, and you should take the thing that comes from the crystallographer, because these guys know what they do normally, and you can then still get these interactions from the metal ions as pharmacophore features, which nobody else can do. So this will help you. But so what we did now is we did this minimization. So I go back to the original model, go back, and here I am now. So this is the original model that I had generated, two hydrophobics, donor acceptor donor, and a H-bond acceptor here. Okay. So what can we do now with this model? We can copy it to another perspective and do, for instance, screening with it, right? So how to do this? There are two ways to do it. One is drag and drop, and the other one is using a widget. Drag and drop means you take the model here, you mark it, click on with the mouse, and it's highlighted, and then you take it with your mouse and you drag it over here, for instance, to screening. This is one way. The other way is to use the little copy to other perspective widget. This one. This widget here, you can place it wherever you want. This has three symbols. The first one is always the molecule. The second one is always the pharmacophore, and the third one is the binding site. And when you mouse over them, you see here on the lower part, data exchange. What happens? If you mouse over, you see data exchange. If there are ligands completely selected, that is where it's copied to some user-specified perspective. So if I want to copy the pharmacophore to the screening perspective, I will click on the middle widget here. And then this opens this little pop-up window, and you can copy it to the screening perspective, for instance, or to the alignment perspective. I copied to the alignment perspective because I copied it already with drag and drop to the screening perspective. And when you look now here, you have alignment and screening. You have a little 1 in brackets. This means there's one object in the alignment perspective and one object in the screening perspective, right? Okay, now let's open another X-ray structure. Let's open 1KE6. So I type in 1KE6. I say download 1KE6. And then she will ask you, what do you want to do? Do you want to discard or store it? I say discard. Just get rid of it. And now she has downloaded the X-ray structure 1KE6. We can zoom in. She recognizes all the features. We create the pharmacophore model. And we see, this is also a kinase inhibitor, CDK2 kinase inhibitor. We see some more features are coming up. We have like now 3 hydrophobic groups. We have still the donor acceptor donor triade, and we have 2 H-bond acceptors on 1 oxygen of this sulfonamide. In this case, it's not a sulfone, it's a sulfonamide now. Okay, so great. I could copy the pharmacophore model to the screening perspective, but I don't want to do it because I know from experience that the X-ray structures are not in the same coordinate space. So if I would do then screening, then hits that would be retrieved by the 1K6 would be in one coordinate space, and the one by 1K7 would be in the other one. So therefore, I want to align first the 1Ke6 pharmacophore to the 1Ke7 coordinate space, for screening, and then put it into the screening perspective. So therefore, I copy this pharmacophore to the alignment perspective. So we copied this pharmacophore to the alignment perspective. Then we switch to the alignment perspective. And now you see what I told you. They are not in the same coordinate space. Up is 1Ke7, below is 1Ke6. So this is just some mistake that the crystallographer did not take care to align the proteins in the right way. But it's no problem for us. We select 1Ke7 as the reference by highlighting it and clicking at the little lock here. Now it's red in the window up there. So the reference is set. Now I select both of them with the mouse, left mouse. And now all of a sudden you see there are more buttons active here. The lock button is no more active because one is locked already, but the next one is align selected elements. So I will now click this button here. And now 1Ke6 is aligned to the coordinate space of 1Ke7, right? And there's also a nice little button here to help you to center your thing to the best optional view. So you press this button and then it will just put this nicely for you. And this is the alignment of these two models. And now you can use the widget again to copy the pharmacophore to the screening perspective. In the screening perspective, I have now 3 models. I had copied 2 times 1K7, so I can delete one of them. To delete a pharmacophore from the screening perspective, you just highlight it and you press this button here, delete pharmacophore. I have 2 models that are on top of each other. And I just want to do the same thing with a third protein in this series. So therefore, I go back to the structure-based perspective and I take 1KE5. Download 1KE5, discard the changes, zoom into the box, create the pharmacophore model, and I get a nice model also here. It's a sulfonamide. On the right side, on the left side, it doesn't have any substituent, so it's a single hydrophobic feature. Again, I want to check first if this is aligned in the correct space. If not, I can align it. So therefore, I copy this model to the alignment perspective first. Then I go to the alignment, not aligned. So I still then take 1KE5, all of them, and I align them to each other. And now all are aligned. And now I move 1KE5 also to the screening perspective. Now in the screening perspective, I have 3 models that are aligned on top of each other in the coordinate space of 1KE7, right? Now let's do something. I do want to do some screening. So what do I need for screening? The pharmacophore and a database of molecules, right? So where do I get this database? You can generate them. What you need is a list of SMILES or an SDF file or a MOL2 file. And then you need to convert this into the Ligand Scout database format, the so-called LDB format. And this is a multi-conformational data format that has for each conformation the pharmacophore stored for each conformation of each ligand, plus feature counts, plus 3-point and 4-point pharmacophores for rapid pre-screening. So this LDB file gets a little bit big, but still manageable. On a technical side, it is a subdirectory that contains a lot of files, the indexes, the structures, the coordinates, the pharmacophores. So don't mess around with this directory. You can look into it, but don't change anything, otherwise you corrupt the database. But you need to know it's a directory. So we have provided you already with some databases. In the tutorial data material, you should have databases ready for screening. There must be somewhere an LDB file that is called, for instance, CDK2 actives or so. So to load the database, I press this button here, load screening database. And now you need to look for it. I don't know where they are on your computers. You need to find them somewhere. I know where my databases are. They are in users shared, data shared, LDB.
Ligand Scout material.
Ligand Scout material, yes. Material for course, maybe. And under databases. So you should have something like CDK2 actives.ldb, CDK2 inactives, true inactives, fragments for tutorial, and so on. Did you find them? Not yet. So who found them? You found them, right? You found them. So where are they? Under? Okay, desktop.
But we have a link on this one to download.
Yes. Okay. Okay. So those who have already the databases locally installed on your computer, you just now select one here, and I would select the the actives here, CDK2 actives. Select database. And then there's another database of molecules that are inactives, that have been tested on this CDK2. And I can also load this database. File, load, no, sorry, here, inactives. So, do we all have this ready? If not, then I wait a little bit. It's on the desktop. So you need to go file, when you do this file open, you need to go to the desktop, material, ligand scout material, and then you will find under databases, you will find these LDB files. And you should load two of them, the LDB CDK2 actives and the CDK2 inactives. Yes?
I have because I don't have the license, like I have the demo version, so you cannot do this ligand-based stuff. No, because I didn't see anything, like I have the structure base, so I have
Yes?
the Pharmacophore, but when I go ligand-based, so it's probably locked.
No, this is, no. You need to put in material. You can do material. You can put molecules in it. You just say ligand set, add molecules,
Okay.
add molecules to training set, and then you just put.
Okay.
Yeah,
So I
yeah.
thought it would get from
No.
my baseline.
Oh, you also can. You can. Yes, you can
What's
copy.
the difference between demo or
The
classic?
demo, you cannot not store anything.
Store anything?
You cannot store anything in the demo.
Okay.
But you have a, when you use the serial number, you can.
Which serial? No, here.
No, the one that he has over there. You have the serial number. Who has the serial number at the moment?
Yeah.
No, but this is not the full one. It's a 20-digit number.
And
Here it is. Here, help about license information.
Okay.
And then you say activate,
Ah,
and then you put
okay.
it. Okay. So are we all ready? Do we all have 2 databases loaded and 3 pharmacophores loaded? Now, one more very important thing. Very important. We have actives and we have inactives. And we want to tell her that the inactives are inactives because we want to help her to generate automatically ROC curves to analyze the results. Have you heard about ROC curves, receiver operator characteristic curves? Yes. So you know this is to show the performance of a model. Okay. So to tell her that this is an inactive database, a database of inactive molecules, you click on this little symbol here that is green, and then it will turn red. You see, now it's red, and this means this is a database of decoys, so-called decoys. If you click another time, it will be inactive, so the database will not be selected. If you click another time, it will be green again, which would tell her these are active molecules, but we know that they are inactives. So, okay. Now, what we will do is the following. We will do a virtual screening of these 2 databases and find out how many actives the models retrieve and how many inactives. So, and for doing this, we press the screening button here. Okay, so it's finished. Are you finished also? How many hits did you get? I get 15. 15 out of 664, it says. 17. And now what I can look, are these actives or inactives? Because here in my column, I have if it's active or decoy. So I have retrieved 11 actives and 4 decoys. I can look a little bit into more detail in the decoys here and see if they are active or not. And what I see is that these molecules that are called decoys are still 1000 nanomolar, which is 1 micromolar. So I would not say that these are inactives, right? These are still actives. 1 micromolar hit is not bad, right? So this means that there is a little problem in our databases of so-called inactives. And therefore, there's another database that says true inactives because they are filtered. Because then I separated them, right? But for the moment, it's enough. What you have seen is the following. You have seen that screening these databases with these 3 pharmacophore models was pretty fast, right? It took a few seconds, and you get this hit list, and you see which model retrieves which hit. We see this here, the matching features. We see the pharmacophore fit score, and somewhere there is also the pharmacophore match. So all the molecules were retrieved by model 1KE7. Interesting. Why? Why do we think it's by 1K7? Well, look at the list of your pharmacophores. What does she do when she finds a hit? When she finds a hit, she does not screen with the second model because it's a hit already with the 1 model. So 1K7 is the first in line. So first she screens with 1K7. If there is no hit with 1K7, she screens with the second one, which is 1K6. If she doesn't find a hit with 1K6, she screens still the molecule with 1K5. And if it's not by either of them, then it's a non-hit. In this case, to save speed, to save time, we ask only to stop the screening once you have retrieved a hit. But there's also a setting where I can ask her to screen all pharmacophores. And this is this little Boolean operator window here below. You can put in a Boolean operator. What are Boolean operators? Boolean operators are or, and not, for instance. So you have 3 pharmacophores named 1, 2, and 3. So you could type in a Boolean operator 1 and 2 and please see here, this little red light is showing up. 1 and 2 and is not complete. Only if you say 1 and 2 and 3, the light turns green. The Boolean operator is okay. So what would this mean? This would retrieve hits that fulfill all 3 pharmacophores. Let's try. Do we find molecules that are hits by all of them? It's a little bit slower now because you see she looks at all. And yes, we find 4 molecules that match all 3 pharmacophores. Great. Great. So these are probably top hits, right? So remember, when you have your challenge, you can do this. You can generate, if you have X-ray structures of your ligands, you can generate and ask her to find ligands in the big set of molecules that match all these pharmacophores. This is very selective, right? This is a very selective method and useful if you have big databases. Yes? Yes, exactly. Absolutely. So what can we else do? There's another thing what we can do. Listen, this is undocumented. This is an Easter egg that we never put into the documentation. But you can put in all into this Boolean operator. You will not find this in the help, but I tell you all. And then you do the same thing. You screen. And this will retrieve all hits for all pharmacophores. So you will find a hit, these 4 molecules, you will find them 3 times in your hit list because they are retrieved by one model, by the second model, and by the third model. So the hit list is much bigger, right? So now I can press this button here and I will get a heat map. I pressed this button here, which is the button for the ROC curve normally. I get this representation. What does it show us? This representation shows us which model retrieves which compound. And are there some unique hits that are only retrieved by one model but by none of the others? So this is very, very helpful when you evaluate, when you build models, a lot of different models, which you should do. You should build a lot of models and then evaluate them on your test sets and then find out which one you use for production, right? For the screening in the big library. So what do you learn from this here? What do you learn? You learn that one pharmacophore is the most selective one, which is model number 1KE6. It retrieves 7 hits, right? Model 1KE5 retrieves 9 hits, and model number 1KE7 retrieves 15 hits. We can even color according to decoy and actives by just pressing this button here, highlight actives and decoy. And now we see the green ones are actives, the red ones are decoys. Even the most selective molecule, pharmacophore, sorry, even the most selective pharmacophore retrieves 1 decoy. 1 decoy out of 600 is not so much. And we already saw that this decoy has 1 micromolar, so it's not a real decoy, right? But this helps us, again, this little heat map here helps us enormously to evaluate the quality of our models. Yes? It depends. Yes, calculated enrichment, yeah, but it depends also what you want to do. Imagine, for instance, you have a model that retrieves only 5% of the actives, but by no way any inactive. And then this is model A. And then you have model B that retrieves 60% of the actives, but 10% of the inactives. Now, this depends when you will use which model. If you have the compounds in-house already, and you only need to narrow down a little bit because you don't want to screen all of them, you will take model B because you want to retrieve the highest fraction of actives, and you don't care if you retrieve also some inactives. On the other side, if you have the large chemical universe that you can buy, you prefer to buy a small fraction of molecules and you want these molecules to be active. So you will take model A for that, right? So there is no answer fits all. It's always depending on what is your meaning what do you want to do, right? This is important to remember. But of course, you can calculate all these values. And when you use this, when you only use one model, for instance, here, so I just select 1K7, and I do the screening now again here, I can generate a ROC curve, and it will show me the ROC curve plus the enrichment factor, the area under the curve at 1%, at 5%, at 10%. So this gives you this curve here, and you see, I mean, it doesn't look too bad, but it also doesn't look too good. So it retrieves, this model retrieves roughly 35% of the actives and only very few of the decoys. And again, so the enrichment factor is 15, 13, 13, 13. And area under the curve is 1, 1, 1, and 0.65 at the end. So it's not bad. Actually, it's not a bad model, right? And remember, this is just pressing from the scratch, no optimization, nothing, right? Okay. Okay, so now we have learned how to build structure-based models from ligand protein X-ray structures. Could work also with cryo-EM or NMR. What is the next thing we want to learn? Because, I mean, probably what I would suggest to learn is apposite pharmacophore modeling. Look for additional features that a certain ligand might not fit, but might be there in the protein, right? So for this, I go back to the structure-based perspective. And I would say I go back to 1Ke7 because I have aligned everything to 1K7. So if I do want to do additional modeling and screening, I want to be in the same coordinate space. So I say 1K7, discard the changes, and renew it. And then we have it here. Now you can do a little trick. You can trick her. You can ask her to find cavities without having the ligand there. So we need to delete the ligand. Right mouse click on the yellow box will delete the ligand and the box. Now it's gone. She doesn't know anymore that there was a ligand. Now we will use the pocket finder of Ligand Scout to find druggable pockets. And this is hidden under Pharmacophore. No, it's not Pharmacophore. Where is it? Molecule. Calculate pockets. Yes, thank you. Molecule, calculate pockets. Of course, there's a tutorial card for this. You can run this. So now what she's doing, she's putting a grid on the entire protein, and she has an algorithm built in that looks at each grid point and checks how much light a vector can see that you turn around in all directions. This is the buriedness. Yes? Because you don't have the you have the demo version, right? You need to put the you need to activate the license. Then it will work. Yes. Sorry. Who has the license serial number?
Yes.
Okay. Here, take it. And you go to I'm not involved in that. Yes.
Like because I don't have the database here, so
Yes.
I'm just converting like one by one the
Ah.
STF to the.
Okay.
Is there any way to convert the whole?
Yes,
STF
of course. Yeah, sure. Exactly with this button here.
Yeah.
So you need just an SDF file with all.
Together.
Yes.
it convert-
Yes, exactly. Yeah. So what I know is, sorry, excuse me. What I know, the only thing I don't know the detailed prices because I'm not involved in business. I'm only scientific advisor of the company. But I know that they have academic discounts and that the license allows for unlimited activations at this university. So you can, also the students can use it. So this is, you pay, it's a yearly price, what I know, but it's not very expensive, and everybody can use it. So, okay. So what she has done now, listen, she has found pockets. Were you able to do this? So what she does is she also tells you which pocket is big enough that you could do modeling in this pocket, and she turns it into orange. And there's other pockets here that are not orange, like this little black thing here, gray. And this is based on two parameters. One is the buriedness, how deeply buried is this pocket, and the other one is the thresholds of the size. What is the minimum size that I need to have to put a ligand in there? And it must be buried. It cannot be on the surface, because on the surface you can put everything, right? So if I go down with the buriedness, you will see that all of a sudden there's much more appearing, right? Which makes no sense. So I go back to the default here. And if I make the threshold smaller, you see that also the pocket that is small is considered as drug-like, druggable. And this is also not good. So I just go back. Then the next step is, yes?
If it's a geometry technique to find the pockets, or?
Yes. So what I think I didn't finish to explain it. It's you have the grid points, and at each grid point she puts a vector that goes into all directions and measures when it bumps into the protein. So then you know exactly, okay, the gorge is like this, and all the other round is protein. And then for each point, she does this, and then she looks how many points are close to each other that have the same kind of thing, and this is then the size, right? So it's a very simple but fast technique. So now I want to make a binding site here. So I click on this, and when I click on this yellow-orange thing, it turns green. And then I say create pocket, and it makes this environment, this kind of yellow box. I can click on the yellow box, and now I am in the binding site here where my original ligand is sitting. But I don't have any pharmacophore features. And now I can create the so-called apposite pharmacophore. And for this, you go to Pharmacophore, and you say create apposite grids. And now she does this thing that I described in my lecture as this Grail approach, right? She looks at the grid points and calculates at all grid points probabilities for all different interactions. And she calculates the buriedness and the size. And so we get this kind of thing here. This is now an isosurface that connects all points in the binding site that are approximately 1.2 or 1.5 angstroms away from the protein. And these are points where there could be heavy atoms that could make pharmacophore interactions. So it's not exactly the binding pocket, but it's a smaller area, right? And each of these points, I could now put manually a feature, or I can ask her to find the best solution. And I can look also for the potentials of these different features. If I click here on HBA, I see the regions where there would be H-bond acceptors. I see the regions where there would be donors, because there are acceptors in the protein. Positive ionizable, negative ionizable. Very small little group here. Aromatic features, hydrophobic features, always, almost. So, okay. This, and you can adjust. You can adjust with these sliders. You can play around also to set thresholds for the features if you think that you don't want so many features. But the other way around, when you create, you can also set these defaults here. When you click now create, you get this window that shows up here, and it says H-bond acceptor. So you can select each feature, and you can ask for a maximum number. You can say unlimited, then she will put all of them, or you can say I want only a few. And if you only want the best, you say 1, right? In this case, I would start maybe to ask 2 as a maximum for all of them. Maximum 2 donors, 2 acceptors, maybe 2 positive ionizables, 2 negative ionizables, 2 aromatics, and 2 hydrophobics. And then you can press OK, but please remember one thing, you can do the same thing also from a structure-based pharmacophore where you have already a ligand in the binding site. You can still analyze around and add apo features around it, and then you click this on here, append to existing pharmacophore, if you want to use the structure-based model and add some additional features. Or you build it incrementally. You first start with the hydrophobics, then you look at donors, etc. So you will append, you will not delete the pharmacophore when you press append. In this case, I have no model in there, so I just say OK, and I look what happens. So these are the features here that she put on. And I can just make the surface grid invisible here, and now I see the features. So this would be the 2 best hydrophobic features, the 2 best donors, the 2 best acceptors, and so on and so on and so on. And so what we see here is that this pharmacophore model is a little bit different from the model that I was using for screening. I can put it back. I can go to the screening perspective and select the 1KE7 model and put it back to the structure-based perspective. Proceed. Do you want to replacing it? Yes, I want to replace it. Now I have the structure-based pharmacophore model. I have replaced the APO model, but I can recreate it. I say create, and I say append to existing pharmacophore. And I say OK. And there we go. And what you can see now is very interesting. It's a little bit maybe crowded here, but you can see that these hydrophobics are in the area where there were already the hydrophobics. The donor acceptor donor is here. There is another donor and acceptor package here. So it is now a model that I can use to do virtual screening with additional features that I can, but I do not need to fulfill if I don't want, right? So this would help you to identify additional pharmacophore features in your binding site. Okay? Good. So we have approximately 45 more minutes, right? I'm thirsty. Do you want to make a break, or shall we continue? Continue? Okay, I just need to drink something. Where's my water? Here. Ah, yeah, oh yeah, sorry. Where do you turn them on? Yes. Better? Okay. I want to show you docking. Docking is very easy in Ligand Scout. There is built-in Autodock and Autodock Wiener. So what I will do is I will just delete this model. So I select everything here on the left. and I delete it. And I use a renew 1K7, and I will use this for docking. So again, for docking, either you have already an X-ray structure where there is a ligand, then you have your binding site already, the yellow box. If you don't have it, you would search for the let's do this. Let's do this again. I want to dock something in an empty pocket. So I just delete this. Oh, sorry, not like this. Go back. I delete the ligand here. Right mouse click. I do the molecule create pocket, calculate pocket. I click on the pocket. I say create it. And I zoom in. Okay. Now I need a molecule for docking. Where do I get a molecule from docking? Now I have a binding site that is ready for docking. You can, for instance, draw a molecule. You can draw it. You can just take the editor here, the molecule editor, and draw a molecule. Any molecule that you want to dock. Did you see the little symbol here for the editor? Let's start. I draw a molecule here. Undo. This is a double bond. Another double bond. Nitrogen. Oxygen. Nitrogen. Aquatic ring. Okay. Maybe this is a good molecule here. Maybe I put another bond. Okay, so you can give a name to this molecule. I say whatever, TL1, first idea. And then you say insert. When you do insert, she will ask you, create a library of molecules. So this will be the first of a library. Replace the core molecule. If you have a core molecule in there, it would replace it, or just inject only. And I say inject only. And now it is somewhere, but not, of course, in the binding site. It has been already converted to 3D, so I don't see it at the moment. There it is, somewhere outside, right? Because we didn't tell her where the binding site is. She should know, but we didn't tell her. But now we can dock every molecule that is visible, every small molecule that is visible. You can put a lot of small molecules in there now. Then you can do the docking. And docking goes very easy. It is like this. You go to molecule, dock ligand, and then you can select autodock, autodock Wiener, or Wiener XB. Wiener XB is Wiener with halogen bond. I like very much autodock Wiener because it's fast and reliable. Okay. Standard parameters, she asks you what do you want to do, how many exhaustiveness, and so on and so on and so on. Just use the default. And now she docks this molecule into the binding site and ranks the solutions already according to affinity. And they are all in the binding site. And this one now here, the injected molecule, I can delete it because I don't need it anymore, because I have all the docked ligands now, right? So did you see how easy this was, doing docking? This is really, really user-friendly. So you could also use docking in your challenge to analyze the hits that you get, for instance. What can you do? How can you analyze? So you get the affinity calculated by Autodoc Wiener. What you can do is you can, for instance, do an energy minimization. You go to library, minimize MMFF energy here. So this will minimize the entire library. So this is a sort of add-on relaxation of the docking. And then there is another function in Ligand Scout. She can predict binding affinities based on entropic and enthalpic properties. It's a quick and dirty approach, but it's very, very useful. You can go to library, predict, calculate binding affinity score. And there's a new column that comes up here with the binding affinity score. Negative. The more negative, the better. Then you can analyze how many pharmacophore interactions each docked pose makes. It's the same molecule. We have 9 different docking poses. This is under library. Calculate interaction feature counts. So this shows you how many pharmacophore features each pose makes. In the first column, you see the total number of interaction features, 7, 2, 2, 1, 3, and so on. The interaction features hydrophobic, X hydrogen bond, and so on, and so on, and so on. These tables, once Ligand Scout shows a table, there's always a relational database behind. So you can do sorting of this table, you can do filtering, you can transform numerical to alphanumerical, you can add more decimals and so on. So there's a lot of functions. When you right-click on the header of these columns here, you see this says it's a numeric, and you can add or remove comma after comma. You can change the sorting to ascending, descending, or none. You can show or hide the column. You can add additional properties to this table. So there's a lot of things. And you can do plots. You can plot these properties. When you go to library, you can say, for instance, I want to have a parallel coordinate diagram of my library. What is this parallel coordinate diagram? There are some features that are not important. The number of conformations, I don't need it, right? So with these 3 buttons here, I can select properties that I don't want. So let's first deselect all. Okay, exclude. And now I want to include the affinity from Wiener, the binding affinity score. I want to have the interaction features, and I want to have this one here, aromatic I don't need, RMSD. Okay. And now when I say OK, I get a plot here that shows these things. So I see the binding affinities are all low. Binding affinity score, and I can filter here with this little slider. So I can just go up and go down, and I see here immediately which ones are remaining. Right? So actually, I want really only the best ones. And I want a minimum of like, and then I have already selected my best pose, and this would be this one, because it has a low binding affinity, a low predicted affinity, a high number of features, and a relatively good RMSD value. So this would be the best one, and let's look at it now. This is this conformation here, right? So this shows you that you can very, very quickly go through a large number of docked poses and select the ones that you want to use, right? This is one little thing. Another thing that I want to show you is how you can modify your ligand in the binding site to get a better binding affinity value. This is great. This is a great thing here. Look at this. You can do molecule show binding affinity surface. And this shows you now how the ligand, which parts of the ligand contribute favorably to the affinity and which are unfavorable. Green means it's good, red means it's not good. If it's orange, it's a mix of good and not good. And this is typically H bonding, because when you do an H bond, it's good for enthalpic reasons, but it's not good for entropic reasons. So you need to desolvatate first, and then you make the interaction. So mostly this is orange. Okay, so, and you have this little this little pie chart here that shows you a predicted binding affinity. And this would be a predicted binding affinity in the micromolar range. Now let's try, and you can do this with your molecules that you docked, your best pose. Try to modify the molecule to make it a higher affinity. And you can store all of your ideas into the table. And I show you how you do it. You can do 3D editing of the molecules just by clicking at an atom, for instance, a hydrogen, and adding something. You click on the hydrogen here, and you go to the little periodic table of elements, and you add, for instance, a chlorine. So did this change something or not? Didn't change anything, so it's still the micromolar thing. But you know what? I save it. So you can say add to library. Then let's see. Let's make a pharmacophore feature here. So you see the pharmacophores. Okay, so this is quite interesting. Maybe there is space for some hydrophobicity here. Let's see. I put another methyl group here, carbon. Only minimal beta activity. Add to library. And so on. So you can play around here. All of a sudden I got a little bit better. So, and you see when you get better, it turns more green. First it's orange, which is not good. If you go to the left, to the millimolar, it would turn red even. The more you get to the right, the more green it is. And when you are nanomolar, it's already green. And when you are in picomolar, it's dark green. Best you can do, right? So try a little bit. Try to modify your molecule to make it better. What you also can do is you can load any X-ray structure and calculate the binding affinity and try to find out how to modify the molecule to make it better, right? So these are all things you can do interactively. I think what is really one of the strengths of Ligand Scout is that it's so fast. You can undo things and you have a lot of possibilities to try out things because the screening is so fast. You can play around with the models, do a screen, redo the screen, redo it, and so on and so on and so on. Okay, so we have covered now a lot of things. We have covered structure-based, virtual screening, apposite modeling, binding affinity prediction. What else do we want to do? You give me an idea. What else do you want to see? Do you want to see ligand-based modeling? Yeah? Let's do ligand-based modeling. And let's add a ligand-based model to our screening to see if the screening finds other hits, right? Okay, so what do we need for ligand-based modeling? Of course, we need ligands. Yes. So we go to the ligand-based perspective, and there's nothing. First, we need ligands. So do we have some ligands? Yes, in the tutorial data set, there are some ligands. And to put them into the thing, you go to ligand set, add molecules to training set. Ligand set, add molecules to training set. Of course, you could also drag and drop them. If you have the window open where the ligands are, you can drag and drop them into this. But what I suggest to go to the now to the ligand scout material for cores, and you go to ligand-based modeling. And I have a file here that is called CDK2 actives SMI. Do you have this file? This is a SMILES file of active ligands. So it's like 36 ligands in SMILES format. Did you find them? Okay. So now we have this table here, all the names of the molecules that are in the SMILES file, and we have a 2D depiction, but we don't have a 3D depiction. Why? Because SMILES doesn't contain 3D information. And SMILES is just a connection of the atoms. So the first thing that we need to do is to do ligand-based modeling is generate 3D structures and conformations, right? We need to make conformation analysis. And to make it easy for you, in Ligand Scout, we have here these little buttons, 1, 2, 3, 4, 5 buttons that you can press one after the other. This is a workflow. It is exactly described on the tutorial sheet. So please, after this lesson where all your brains will smoke afterwards and overheat, calm down and look at the tutorial. So the first thing is generate conformations for ligand set. And important, they need all to be training here, right? So then there is a window that opens and asks us what settings do we want to use. And there is 2 extreme settings, the fast and the best setting. You can use whatever you want, and you can change all the parameters if you like. The generate conformation is this little button here, right? This button. So I just use this and I say OK. And now Ligand Scout, she transforms each of these SMILES into a 3D structure and analyzes all conformations and stores them. Okay, she's a little bit hesitant on staurosporine. Okay, great. Okay, so we have now an additional column that tells us number of conformations, right? So each structure is now in 3D, and each structure has a number of conformations. And now we can ask her, the next thing we ask her is to cluster them, to make a cluster analysis, because we don't want to put all ligands into one model. Because what happens if you put all models into one ligand, all ligands into one model? You will end up with a pharmacophore model maybe with 2 or 3 features. And this is not what we want. We want several high-quality models. So we want to cluster first and then build pharmacophore models for each cluster separately, ligand-based models. Okay, so the next thing is cluster analysis. We press this button here. And these are the default settings. To begin with, just use the default settings. Okay. And now she has clustered our 36 molecules according to what? According to radial distribution fingerprints of pharmacophores. So this is a pharmacophore clustering. It's not a scaffold clustering. It's a pharmacophore clustering because we want to put compounds together that have a high chance to give one consistent pharmacophore. Not only everything together to have a model with 3 features or 2 features, but a few clusters with a lot of pharmacophore features. And now we can, we see here cluster 9, cluster 14, 10, and so on and so on. So we can rank the cluster ID to get an idea about how many clusters we have decreasingly. So we have 14 clusters, obviously, in our data set with this setting. So I can play around with cluster size and so on. But it's okay to start with this. So I have cluster ID and cluster size as a property. And now the next trick is to build for each cluster a unique pharmacophore. And to do this, Ligand Scout, she always takes molecules. She doesn't look at the cluster or something. She takes molecules that are training. And if you press now generate pharmacophore, she would take all molecules. So we need to select only one cluster as training and ignore all the others. And for this, there are 2 buttons. This first button here, the gray one, the next one, will make all molecules ignored. Then you select one cluster that you want, and I would say the cluster with 5 members here. And I press this next button, and this makes select cluster ID as training. And now these 5 molecules are training and all the rest are ignored. And now I can press the next button, which is generate a pharmacophore model out of these 5 molecules that contain one cluster, that are a member of one cluster. And the only thing I have to do is give it a name. So it says model here, so I will say model cluster 5, no, cluster 10. Was it cluster 10? No, it was cluster 13. But you can do whatever you want, the name, right? And I can select the pharmacophore type, the scoring function, leave it to pharmacophore fit and atom overlap, because this is the best one. There is only pharmacophore fit, relative pharmacophore fit, only the spheres, Gaussian similarity, but the pharmacophore fit and atom overlap is the best one. And then use merged feature model, because this will generate a model with optional features that a few molecules might not have, so you can have a difference in SAR. And you can ask of how many models you want to build. And in this exercise, I just want to have 1 model, but you can ask for several models. Right? So in this default, it's 10. I just ask for 1. And I start the process. And now she does overlay of each conformation of each molecule and finds out which are the best overlays. And this takes a minute or so. If the data set is bigger, this computer's slow, it takes longer. But it should not take too long, because it's all built on being interactive. So it should be finished after less than a minute. And she will generate the pharmacophore model. And I can immediately use this model then to do screening and see how well this model performs. So imagine, I mean, we have 22 by 100 by 78 by 100 by 100. So it's 100 times 100 times 78 times 100 by 22 alignments. So it's an incredible amount of alignments that she needs to do. And this is why it's still not finished here. Are you finished already with yours? Okay. Oh, your computers are better than mine. Okay, you have different. Okay. No, I will just leave it here. I don't know. But what those of you who have already a pharmacophore model, just take the model with the widget and put it over to the alignment and try if you can align it to 1K7, for instance. Would be very interesting if you find features that match. Okay, now I have my model here. And look, wow, look at this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features. So 4 of the molecules fit 10 features, and one just fits 6 features. So this is quite amazing. So I will do now the same. I will move this model here to the alignment perspective. So I take the model, move it to the alignment perspective, go to the alignment. 1K7 is still, I put this 1K7 as the reference. I select both of them, and I try if I can make an alignment. And it works. I even can make an alignment. So this means here that there is some similarities between these two models. Right? Ligand based on one side that does not know anything about the protein, structure based on the other side. And now I can take this model and put it to the screening perspective and have it aligned already correctly to the thing. So screening. Okay. Let's do another one. Same procedure. First, I press the gray cluster button to make all ignored. Then I select another one, maybe cluster 12. Make it the requested. Generate the pharmacophore model, change the name, cluster 12. Okay. Go, calculate. You are probably finished already. Yeah. I see. I need to get a new one. This is a good argument. When the computers in the computer room are faster than your laptop, it's a good argument to get a new computer.
I'm waiting for
Yes. Okay, I got another model here. A model with 6 features. And 2 molecules fit all the 6 features. One fits 5, and the other one fits 4 features. Same thing. I put the model into the alignment perspective. I try to align it to the 1K7. And also here we can get an alignment. Perfect. I take the molecule, the pharmacophore, and put it over to the screening perspective. And so on. And so you can do this for all of your ligands. But what I want to do is I want to stop this now here, and we go back to the screening and do again this analysis with the heat map and check if these ligand-based models were able to find other chemotypes than the structure-based models, right? Now, in the screening perspective, I have like the 3 structure-based models and the 2 ligand-based models. And I do again all, and I run the screen. And this might take a little longer now, because it's 5 pharmacophores screening all on this, all molecules, on the actives and the inactives. Yeah, I need an M6. You are absolutely right.
I mean, M4 is still pretty much faster.
Yeah, you have the M4? Oh, yeah, wow. But is the M5 already out?
Yeah. Should be 5 Pro.
Ah, okay. But then we should wait for M6. But what is really amazing is the energy consumption. You can run this machine a whole day, and it will, I mean, when you use Ligand Scout, it will kind of suck out energy, but normally for normal working, it's amazing, right? Yes, 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 yes. So it tells us it will take still 1 minute and 10 seconds. And it takes a little longer because there are also optional features. I didn't mention this, but probably you saw it yourself, that some of the features look a little bit different. They have this checkerboard kind of thing, right? These are so-called optional features. They might be matched, but there will be also a hit retrieved if this feature is not matched by the ligand. And this is a directed optional feature. And you can also give her the freedom to decide which feature she wants to make optional. But this, in this version here, gets then slower. If you ask for one optional feature, it's okay. You maybe take 10% more search time. If you ask for two optional features, it will get slower. It will probably take 30 or 40% more search time. If you ask for 3 or 4 more optional features, forget it. Because it's a combination problem. She needs to find out which combination with this algorithm. In the next version of Ligand Scout, this has changed, but it's not yet out. So and I'm very curious to see the heat map now, because I suspect that there will be some pharmacophores that retrieve a lot of false positives, especially the one of cluster 12 that has only 4 required features and 2 optional ones. Now it's finished, and you see here the matches. So these matching features is all pharmacophores here show, and they are also linked to each other. So if you click, you see which feature it is. Right, so this is all linked, and also in the 2D depiction, if there is a one. So now let's look at the heat map. Here is the heat map, and it's a little bit bigger now, of course. So and I also, wait a second, I also want to color highlight actives and decoys. Oh. And I want to sort X and Y axis. So, so what do I see? Let's interpret this. So you have here model cluster 12 retrieved 247 molecules, a few actives at the top, but a lot of inactives that the other don't retrieve. What is the difference now between model cluster 13 and cluster 12? Cluster 13 is better. Not really better, maybe not, because look, there's some actives in the back. So the total actives, that's not so good. So the structure-based are really the best ones still. And do we find any molecules that we did not find with the structure-based? Yes, we find a few. This, for instance, this hit here. This hit we did not find with structure-based. These 2 hits we did not find with structure-based, right? Also these 2. So again, so this is exactly the case that we had before when you asked which model will you use for which setting, right? If you have the compounds in-house and you would not test it, it would not make sense. So you better test them, right? If you want to buy compounds, you should not use this model, right? So this is really helping a lot, I would say, in your evaluation. And also you need really to make sure that the inactives are true inactives, which in these decoys is not the case, because we know that there are also macromole activity. Okay, so I think we are almost finished. I will just show you, and you can play yourself if you want to do it, the dynamics models, right? We will load in a dynamics trajectory, and we will generate this dynamic pharmacophores, and we can look at these nice pictures. Okay, so for this, we close everything. We say file, close. Yeah, and I didn't tell you, but of course you can save. When you go to file save as, you can save SDF files, you can save pharmacophores, you can save images, you can save 3D images, 2D images, you can save a lot of formats. But you just go to file save as and type in either the extension or you look at the list of file types that you can have and you will see. But now let's go to the MD simulation. So the MD simulation is also in the data set that you have. And for this, I say File Open, and I go to MD simulation, and I start the 1KE7 start PDB. I open it. So this is now the starting structure of the PDB. And I zoom in. And okay, I can stop this hide binding affinity surface. I don't need it. So now I see this. And then I go and I open the trajectory. File, open the trajectory. This is a DCD file. So Ligand Scout will read in charm, amber, Gromax trajectories. And now you can already play through the trajectory here with this little thing. And you see how nice. I mean, the visualization is extremely beautiful because there's interpolation. So it's not this kind of shaky thing, but it's really smooth.
Periodic box conditions by itself?
Good question. That I don't know now. Normally, yes. Normally, it takes the periodic boundary condition that is set in the dynamics. But it might be tricky if you have a periodic boundary condition that are skewed, for instance, or a sphere. This is a little bit tricky. This is tricky. But now I want to show you how to build the pharmacophores. So it is there under Pharmacophore, and there is a point that says MD pharmacophores. And then you say create MD pharmacophores, and then you have a little window that tells you that asks you what you want to do. Do you want to create it for all frames, or do you want to leave out at the beginning, for instance, because it's an equilibrium phase or whatever? In this case, I just do for all. You say create. Every frame, you also can ask for every 10th frame, every 20th frame to have a limited number. And this takes probably half a minute. This is 300 frames. It's not a big dynamics simulation. It's a short one. But then you have all the pharmacophores from the MD simulation. And I will show you what you can do with this. Not only look at them, but really make an analysis of the features. Of course, once you have created them, you can store them, save them, and reread them in afterwards. So this is a special file format. It's called TDF file. Yes, the trajectory pharmacophore.
And can these analysis be done in command line too?
Not that I know. At this stage, no. It's okay. Now we have, look. So we go back to the beginning here, and we can play, and we can see. Look. You see now the pharmacophores features coming and going. So you see, for instance, that there is this second hydrogen bond here that comes and goes. It's not there all the time. Also, sometimes here you have an aromatic interaction. Water, you see water molecules that interact here. Comes and goes. Here's an interaction to the backbone. So it's very interesting. Already just looking at this already gives you information. But you can also create plots and export the data in CSV format for further analysis. So you go here to Pharmacophore, MD pharmacophores, then you have additional things. Show MD pharmacophore plot, show interaction map, show feature timeline. Let's show the pharmacophore plots. This gives you the unique pharmacophores. So this pharmacophore here, for instance, occurs in frame number 46, 54, 59, 60, and so on. right? Oops. How do you go back? Sorry, I didn't know that. I didn't want to do this. Show pharmacophore's plot. This one here occurs not so frequently. This occurs in these ones here, okay? Okay. Now I can put a threshold here. For instance, I want to have only pharmacophores that occur more than 12 times minimum. Yeah, so this is this one, this one, this one, this one. Then I want to see, for instance, this donor here. Is this donor present? Yes, this donor is present in all of these unique pharmacophores. This hydrophobic is also present. This aromatic is not present in all. This aromatic is only present in this one, in this one, right? So this gives you already, you can very quickly go to the frames where a specific interaction is occurring, and you can analyze then what this means. Next thing that you can do is you can make this pharmacophore MD pharmacophore the interaction map. So this will show you, and you can also, by the way, you can detach this and put it on another screen. If you have a bigger screen, you can detach it and put it to another screen. So but again, so here we have now this hydrophobic here, for instance, you see, makes these interactions. This H bond acceptor here, which is then highlighted. No, it's not highlighted in this frame. So you can here see which kind of interactions are by which amino acids and which part of the ligand. And the last plot, you can save this as a CSV file or as an image. And the last plot that I wanted to show you is the feature timeline. Pharmacophore, MD pharmacophore create the feature timeline. Here you see the timeline of your pharmacophores features. So this yellow one is there all the time, the hydrophobic. The other hydrophobic is almost all the time there. The aromatic one is not all the time. One donor is pretty unstable. The other donor is very stable, right? And with this little slider here, you can go through and go to the frames here, right? So this is very interesting. So you can see here, for instance, at this space, there is more frequently. This one is there all the time. The acceptors are a little bit different. This is more stable, and so on. So you can get an idea here about, again, in a pharmacophore dimension, your MD analysis. Normally, when you look at MD simulations, you look at distances. But think of following case. You have an H-bond donor, your ligand, and you look to a specific amino acid. But then all of a sudden, your ligand switches to another amino acid that moves away, but makes still an H-bond. So in the pharmacophore plot, you will see this H-bond. But in the distance analysis, you would not see it because all of a sudden, the distance is not okay anymore for this one H-bond, but it has changed to another one, and it's there. So this is an information that you would never find when you do the normal MD analysis, right? This is why I believe that pharmacophores can help in analyzing MD trajectories very, very much. Okay, what else? I mean, there's tons of other things that you can do. I mean, we have not touched on a lot of other things here. You can look at all these menu downs here, render control. You can change the way the molecules are displayed. You can have you can change this backbone to this view, for instance. There's tons of other things that you can do. Is there anything? Yes, tautomers, you can generate tautomers. Docking, we did dick docking. We did ligand-based modeling. Hey, actually, we did quite a lot. Surface, we did surface, the binding affinity analysis. Yeah, so I think we covered quite a lot in this short amount of time. And I am at the end now. I think you too, right? Are your brains overheating? Or is it fine? You can manage, great.
Very long trajectory that is not straight, so it will just crash.
No, no, it's very stable. It will take a little longer, but it has an efficient memory management. So it does not keep everything in memory, it just keeps the things that are visible. So also tables, for instance, you can load a table of several 100,000 molecules. Will not slow it down. It will just take a while to load it, but once the table is there, it is there, and you can scroll through it very quickly, and so it's, yeah.
I'm an MD person, so I'm used to crashing stuff with just very long.
Yeah, it's not Schrödinger. Okay. Okay. So are there any questions from you guys? Are there any questions from the audience? Is this